Okay, so we're going to talk quickly about Tony Creek Fish Passage Project. This was a project that we implemented last summer of 2023. It was a partnership between the Watershed Group, the Confederated Tribes of the Warm Springs, and Oregon Department of Fish and Wildlife. Everybody was involved in some shape or form, from the project management to the funding to the fish passage authorization and all of the above. And I'll talk a little bit more about that. We're going to give a little bit of background about Tony Creek, some background on the project. We're going to talk about the design, or Steve's going to talk about the design. And then we're going to talk about the construction, the actual implementation of the project, and some of the monitoring that we will be doing post-project. So for those of you who don't know, Roger was telling me earlier he has been biking along Tony Creek since Tony Creek is a tributary to the Middle Fork River on the west side of the valley, just below the flat. And it is a very important clearwater tributary. Middle Fork is, as many of us know, a pretty glacially impacted system, from the Elliott Glacier, the Coe Glacier. And so these low down clearwater tributaries are really important to the native fish in our watershed. In Tony Creek, there are current and historic populations of spring Chinook, coho salmon, winter steelhead, and bull trout, and then also rainbow and cutthroat. And all of those species, except for rainbow and cutthroat, are listed as threatened in the Endangered Species Act. So an important stream. Just a little note about bull trout. Bull trout, generally a historic population of Tony Creek. The bull trout population in the Hood is the only population. The Middle Fork population is the only population in the Mount Hood subbasin, and only population in Mount Hood National Forest. So an important population for the endangered species. There's a distinct population above the Clearbranch Dam, so in Lawrence Lake and in Pinnacle and Clear, and then a population below the dam, which historically accessed Tony Creek. But we haven't tracked them in there for a while. And that is largely all of these species, their habitat, their spawning and rearing habitat has decreased significantly for a number of reasons, but the two biggest are the impacts of logging in the watershed and a couple of fish passage barriers. So I wanted to show you this picture. Does anybody know where this is? This is D. So this is, if you were coming down D Highway to the north, this here is D flat. And this is generally this up above here is where the Middle and East Fork confluence is. This is generally referred to the East Fork until it hits the confluence of the West Fork down below. This is the dam here. This was the Oregon Lumber Company land. This dam here was in place for about 41 years. A pretty major fish passage barrier during its lifespan to everything above on the Middle Fork and East Fork. And a lot of the lumber that came through this mill largely came from the West Fork watershed, but because of the railroad that ran very close to Tony Creek, the vast majority of Tony Creek was logged and brought through this mill. So there's a long history of impact from logging on Tony Creek that had erosion consequences. There was historically a large amount of large wood naturally forming in the watershed that created a lot of great habitat, but a lot of that had since kind of come through in the logging operations and had a pretty significant impact on the fish species there. The other major impact besides the dam down by the D mill was this dam that is a private dam, a private diversion dam. It's about a half a mile up from Tony Creek's confluence with the Middle Fork. This dam was put in 1965. It sends water down to the D mill area. At the time, it was sending water down to a plywood mill, a plywood factory and the mill, and now it still diverts. Just a couple of years ago, they added a hydro right to the water right, and so now it diverts year round. And the water right is for 2.5 CFS, but at low flows in the late summer, Tony Creek has about 4 CFS in it. So if they're diverting their full water right at 2.5, you can imagine that's a pretty significant impact downstream of that. And so it's been considered a full passage barrier and a full upstream passage barrier. There's downstream passage by way of a fish screen for juveniles, but otherwise there's been a pretty full cutoff of the historic seeding above this dam, and there's about 5 miles of habitat above this dam that would be really great for these threatened species in the watershed. And about 14 years ago, ODFW listed this on they have a nice little list of high priority fish passage barriers. And there's been a large focus of trying to get this dam addressed. As of last year, it was one of 2 remaining high priority fish passage barriers, and now there's only 1 left in our watershed. So a win there. So the goal of this project was to restore upstream fish passage at this dam, reconnecting those 5 miles of critical habitat, and increasing the presence and abundance of native fish above the barrier. And so just a little bit of background on how we develop these projects. The Watershed Group, along with all the partners, the Forest Service, the tribes, ODFW, the irrigation districts, Columbia Land Trust, you name it, we come together and we do sort of groupthink project prioritization over time. And Tony Creek was high on that list. We put in a good effort on landowner and stakeholder engagement in order to for folks to sign on to these projects. In this case, the landowner is Green Diamond. It was Weyerhaeuser until several months before we started working on the project, and Green Diamond bought all of the timberland, basically the private timberland that Weyerhaeuser owned in the watershed a couple months before we started this project, and that actually, I think, in a large part was why we were able to do this project. Green Diamond has been a really great partner on the project. And then the dam itself is privately owned, so working with the dam owner as well. We fundraise for these projects, both for the design and the implementation, and we had funding from the tribes, from Oregon Department of Fish and Wildlife, and Pacific Power Blue Sky funding. We hired Steve and Liz with both Water Resources to help us develop the design and the engineering for the project. There's an enormous, really fun amount of permitting we go through for these projects. And then we hire a contractor to implement Steve's design. And then we go into sort of a monitoring and an adaptive management phase to make sure that the work we do is doing what we wanted it to do, and we adapt if we need to. So this is our existing site. Steve's gonna walk you through the exciting technical stuff. I think so, yeah.
Hi, everybody. Steve, the design engineer. Just before I dive into this, just really want to acknowledge thanks to the River Watershed Group, Alex, especially Cindy, and then also some of my colleagues that helped do this design. Did a lot of the heavy lifting, like Liz, who's in the audience, but some others at my office, like Lucas Evans, as well as Curtis Loeb. Anyways, so yeah, this was a really interesting project. Just a little background. It's the existing site. You can see Tony Creek running from left to right here, and you have that dam, as well as downstream. You have like some historic features, like a historic dam, as well as Tony Creek Road. which really locks in the site. And then you have a very high terrace on the left. I don't know who's familiar with the site, but then also before construction is it was also locked in by another like big earthen berm on the right-hand side as well. And then a lot of diversion infrastructure in the floodplain to the sides. And to kind of get a sense of what some of that looked like, obviously the diversion, the intake as well, the infrastructure in the floodplain, the bridge down the stream, and some of the old concrete remnants in the floodplain. So it's full of constraints. Like this, the site had a lot. The biggest one, obviously, was the diversion structure itself. And from the start, with the direction is we couldn't touch it, essentially. We couldn't do anything that our project couldn't extend into its footprint. We couldn't affect its operations or anything like that. And then the bridge downstream. So it was only about 300 feet from the bridge to the diversion structure. So it's a very short reach. And within that is we couldn't really affect the profile of the stream itself. And there's not a lot of room in the floodplain because that has a high terrace on the left. It's got infrastructure on the right. So we couldn't change the alignment of it, lengthen it in any way. So we're really locked into this site. So it's really constrained. And then with our design objectives is, you know, we have to design a project that meets fish passage criteria. And some of the basics ones are we have to achieve jump heights for fish. We have to maintain water depths at various flows. And as Alix was saying, as flows get really low, low flows, especially when they divert more than half the base flows, we're left with only like 1 CFS or cubic feet per second in the channel itself. And then additionally at high flows, the velocities we need to lower them. It's a really steep reach. It's really narrow. It's coming with a lot of energy, and the narrower it is and the steeper it is, the faster the velocity. And we need to slow that down somehow and let fish get up the stream. Since we're running short on time, I'm going to skip slides that have numbers in it, so you don't probably not interested. But basically, with the fish passage, we're also, they have design flows essentially. It is between a certain range of flows, basically above flows that happen more than 95% of the year. Basically, you know, 95% of 365 days of the year, flows above that we need to maintain fish passage, but then also 95 or 5% on the upper range. So there's a wide range of flows that we're trying to meet. And basically also with the diversion structure, when we start getting design, it's like, what are we trying to do? And we're trying to get fish past this structure here. And as you can see, can't really make it. This is in a low flow condition, and flow is actually going under those boards. And to get a sense is they got to get over that somehow. They can't really get through the little slot in between. For your reference, if you haven't been out there, that's about a 2.5 to 3 foot jump there, and the little fish can't do it. And we're trying to meet a 6-inch criteria. So we got a lot of ground to make up. So how are we going to do that? Essentially, this is what it's looking like. There's a big board in the way and flows going under it, and fish can't jump over that. Somehow, either you can go around it or maybe you can go over it. And this is kind of what we're trying to achieve. So when we're trying, I was trying to think of a simple way to show this, but basically, we need to do what the dam is doing, essentially downstream of it, and bring the water level up so fish can swim up to it, ideally swim right through. But if we can't get that high, maybe jump over it. So that's our objective. We also looked at, you know, maybe some ways of getting around it, but because of the constraints, that was just not feasible. So now we know what we want to do. We kind of have to go through the design process, and there's a whole list. And we're kind of, one, we need to get to the design, but also we need to meet some certain milestones along that are stipulated by, you know, the Watershed group, but they got to meet like our funding requirements, our permit requirements. So, but first we got to get the data. that's the site recon. We're going to go out, we're going to survey it, look at the site, get a sense of what we can do, come up with some ideas, collect some topography with, it's challenging. There's not a lot of cell service out here. We can't just go out with the GIS. We have to get total station. So we survey it. Then we have to come back, do a little brainstorming in the field, come back to the office, come up with some ideas and develop some alternatives, and then evaluate each of them, see what's best. And the goal of that is we want to come out with a preferred alternative that we think that we're going to take through design. Then we go through all the design analyses, get your preliminary design, then permit level design that we get all the permits with. Finally make final design, which they'll go out and hire contractors can bid on, and then eventually get to construction. And then all through that, at various instances, we do a lot of outreach and check in with various stakeholders, the diversion owner himself, the landowner in Green Diamond, BPA, one of the funders, ODFW, another one of the funders, and we do a lot of that. Alix did so much of that. That's a real tricky part of this project. I got to participate in a handful of those opportunities, but I know there was a lot going on in the background all throughout, before we even got involved and all through when we were there. And it's a very important part of these projects. But then we developed some alternatives. The first two, like a rough and channel cascade pool, very similar, basically the same. Cascade pool is just a little steeper and includes some resting pools in there. A step pool, that's basically just a series of steps that don't exceed that maximum jump height, essentially, to like make the grade up. And then a side channel, that's literally going around the diversion. But since that would then require taking flow away from the diversion, that affects its operations, or would be perceived to, so that was kind of ruled out. And some of the simple graphics of those, like a cascade pool, I didn't change the slides, so we're going to skip through them. But basically, the preferred alternative was that cascade pool morphology, and the reasons why it was something, one, it provided that fish passage, and then two, it's something that for the basically conditions of the site, the slope and stuff, was actually something that you could expect to see in a natural environment. And then three, also it's deformable, so to speak, as it can withstand some change. There's the beds change over time in streams, and so you can expect to see rocks move around a little bit, but it still functions with a little bit of modification, as opposed to something that's very rigid in its design, like a step pool that requires specific geometries that if a rock comes out of place, that you might not achieve that. The fish passage criteria then it can't handle that change. So those were some of the reasons. And then, as I was saying, is these projects are really tricky. Is this one in particular is we needed to bring the bed up, and but ideally, like I was saying, is we'd bring it all the way up where fish could swim right through that gap. However, what we found as we started modeling this is when we bring it too high, is then we start really reducing more waters than going to the diversion. And when we brought it up high enough where fish could swim through, which was a desire of ODFW to basically accommodate all species, is we found through modeling is that would actually send all the water to the diversion and dewater the creek. So that was a challenge. And then it became more of an iterative process where, like, what's the best we can do? And so it was testing different elevations of that profile and how high could we get, and without dewatering the creek and maintaining the depths, maintaining the jump heights and such. And essentially that was a real challenge, because restoration projects, they're tricky. They often have stakeholders with competing interests, so we had to maintain the flows to the diversion and maintain flows to the creek. So we had to basically make meet somewhere in the middle. And we had to show to ODFW that we couldn't meet all the requirements. But then once we were able to show them that, we were able to bring it down a little bit and meet somewhere in the middle and come up with something where we could get it close. And then maybe we could then work with the diversion owner and ideally come up with a scenario where they don't really need that board on top and say, can we like lower that board? And so through discussions that Alix was having with the diversion owner is we kind of met in the middle and we brought the creek up and we had discussions with the diversion owner where they were open to bringing the boards down. And then we were able to meet the jump heights. So that was one key component of the design. Another key component was the channel design itself. Because once we kind of come up with like, all right, we need to bring the channel up this high, is now we got to design this channel that's going to handle all this flow and not wash out like the existing channel has already. So we need it to be resilient. We need to be resilient to peak flows. We need it to be, to the greatest extent possible, minimize that stream power that's out there because the existing conditions was super narrow and coming out of this creek. So it was basically like a fire hose and it washed out all the bed material. And natural creeks tend to replenish themselves, but there's too much energy in washing all the bed material out, and the dam itself was actually retaining all the sediment coming from upstream. So it was just getting washed down to this hard pan, this very clay layer. And so none of the rock was sticking around. So with that, we made a decision that the bed needs to be very resilient. And we're designing, putting oversized rock so that it can withstand flows up to the 100-year event. We don't want it to go away. And with that is, if you, I'm not going to show you many equations, okay? But good point. So basically, we can measure that with some hydraulic variables, the power of the creek to basically erode stream bed. And rather than look at the equation itself, look at the specific variables. The things that go into it are the channel slope, which we don't really have much control of because we're so confined. And if anything, we're raising it to kind of meet the diversion. The discharge of the creek or the flow. We're not Mother Nature. She's dictating this. But then also the one on the bottom is the channel width. And that is actually something we can do something about. And it's on, for all you math whizzes out there, it's the denominator. So we widen it, we make it bigger, it actually reduces the stream power. So with that is, like I was saying before, on the right-hand side, there's this big mound that's confining the channel, and it's leaving just this 20-foot channel or under pre-project conditions. Well, what if we remove that and we widen this channel? And so that was our plan. We could essentially double the width of this channel and greatly reduce the power of this creek and increase the likelihood that what we put in there is going to stick around, reduce the forces that are acting on our proposed channel. And so that's what our design intended to do, and ended up with something like this instead. And what's that? Not so much. I don't know if we see much spawning. It's more just reducing the amount of power in here, because there's the fish need definitely spawning habitat. That's upstream. Let's just say that, because we want them to get there. But before this project, they couldn't swim through this because it was just fire hose. It would just flush them right out. And so, or not enough water. And so, and to kind of see it, and this is where I get excited, this is the model and the output. And don't look too closely, but see the colors more or less. On the top two are existing conditions. And on the bottom are post-project conditions. And a couple different design flows that we did. But you see a lot more of the reds and yellows and oranges, as those are the higher velocities and higher powers. Not to mention on the top, it's a much narrow stream of water that's running down. But then on the bottom, it's a lot more cooler colors, the blues and the lighter blues. And that means we've really reduced the velocities. And we've, as you can see, we've made it a much wider wetted channel and just spread the water out, spread the energy out. And you can see a little like, and especially on the right, that's a lower flow, but you can see these little circles in there. Those are boulders, large boulders that we also are incorporating into it that are above the water surface and create just kind of shadows and slow water areas, but basically creating those slow water paths that can get up to the dam and then cross over. And then so that's what went into the design, and finally we came and then put all the detail into it so that a contractor could bid on it and build it. And that tried to keep it short. So right?
Gotta help me walk through this part too. So
I guess I could lead into that. So after we did all that, is we put together basically design drawings. We put the details together on how to construct what we were trying to achieve, essentially. How you build a channel, how you put all the rocks in, the step-by-step process of constructing the channel, like over excavating, to the dimensions and the elevations that we needed them to get to in order to achieve that objective. Yeah, and then they went out and built it this summer.
you can see these projects are really engineered so that, which is what we have to do in some of these stream reaches, like Baldwin Creek, where there's infrastructure, where there's a FEMA floodplain mapping, so that we can get these projects permitted and put them in the ground. So the enormous amount of work that goes into the design and engineering is clearly a critical part of this project, or these projects. But so we're just gonna show you a lot of pretty pictures of the process of the construction. This is before, so this is looking up at the dam, and then this is pretty much at the bottom of the reach looking up. But and this is clearly at low flow, so you can imagine. So we constructed this project between August 15th and September 20th last year, so a decent amount of time. We hired Aquatic Contracting to do this project. Let's see. They're amazing, yeah, amazing contractor.
Challenge with construction is it's a very unique situation. There's a lot of on the water. You're always dealing with water. There's a lot of sensitive habitats, and just a qualified contractor that's done this work before and knows what they're doing and just makes a world of difference in project success. And they were really wonderful work.
So this photo, a drone photograph, was taken by Dave Nagengas, the owner of this shop. We've been trying to do a little more before and after photography and video footage from the drone perspective. It's a really great angle. And Dave trialed this out with us. He has a really great video that I couldn't add to our presentation, so sorry, Dave, but you can see Chuck in here and Cindy and I, and this was some pre-project monitoring beforehand, so we knew what we were dealing with to start. The first thing we do, particularly in this reach, we were able to divert the entire project reach through to the diversion to maintain downstream passage for fish that were in the creek. So then we basically dewatered the entire 300 reach that we were constructing. And then ODFW comes in, and some key volunteers like Alexis, the new FID manager. And we salvage all the fish and other aquatic wildlife species that are in that reach before we construct. And we found a really amazing array of species in the reach. You can see they're holding a giant Pacific salamander there. We found a whole bunch of cutthroat and rainbow trout. Here's another salamander. You can see in the bucket underneath there some of the other all juvenile fish species that we found. Some rough-skinned newts, and we found some a lot of coastal tailed frogs. And throughout the project, as Steve can attest to, we probably found 100 of these giant Pacific salamanders in this 300-foot reach. They like to bury down into the rocks, and so they were kind of a constant feature, and we continued to salvage them throughout the project. And there's just really an amazing, diverse, and abundant group of species. This is this berm that Steve has been talking about. You can see the creek is on the other side here, but it was a man-made feature on the landscape that kind of tucked, or that really confined the reach. And so one of the first things we did was take that out with a big excavator. A lot of that soil that was on site we used to raise the road, the access road. And this is sort of in process. You can see how much big rock material was in there. We were able to reuse that all in the construction of the creek itself. You can see how it's changing. We brought in upwards of 1,700 tons of rock in a range of sizes. These very big 4 to 6 foot boulders, some even bigger. A mix that we had created for us, an engineered stream bed mix that had a varied amount of cobbles and small boulders, and Steve put a lot of time into creating the exact specifications for that mix. And then we had a whole bunch of sand, and we'll get to that in a minute. This is Steve's schematic of what it should look like when it's constructed.
Yeah, so mixed in a couple plan set details in here because we have constructed photos. So basically we had to put in, we had to develop these details, construction details, how to build different features. Some of the elements we did were the grade controls or boulder crests that kind of set those grades, and then the actual step-by-step sequencing of building the channel, and then also create the resting pools in that Cascade Pool formation is putting in these big boulder clusters that would basically create small backwater areas and pool areas within the channel, and then it would meander through. So to get a sense, and this also emphasizes how important it is for a good contractor, is they need to be able to look at these cartoon drawings that Liz and I developed. Yeah, you're not off the hook. And then they need to build it and be able to interpret this and build it in the field. And then so when you look at something like this, it's actually kind of looking like this in the field. And then, and putting these things in, and then after they backfill it, you're just like, wait, where did they go? But it's in there.
Yeah.
And it's really in there to like kind of lock in that grade material.
The grade is set down below the grade of the finished stream bed. So those 4 to 6 foot boulders in this big, as the contractor called it after a while, these big frowny face across the bed, because he loved it so much. That's underneath the bed, and then they're filled in with all this other mixture of rock. Then
like the foundation.
It's the foundation. Yeah.
Right.
And there were
Yeah.
4 of those throughout the 300 feet. And they sort of set the grade, and they're pretty bomb proof, so that if there's shifting in the creek over time, which we expect that there might be, that really holds the grade so that the creek isn't going to head cut up and take out the very precisely constructed stream bed.
Was there any bedrock at all?
In one challenging section, we hit, we had to, you saw in this back picture, in this picture here, we are constantly checking grade and making sure that those rocks were placed right where Steve wanted them, so that we could conform to the design. But just downstream, actually, from this spot, we hit some pretty hard pan rock, and really what we ended up doing is chipping it out with the excavator. So we hit that point.
Yeah, it wasn't quite bedrock. It was more like a really hardened clay. So yeah, they weren't able to chip it out.
There's always exciting challenges, unforeseen as you're constructing.
It's kind of like just the general channel. It's in order to build this channel, it's not just dig a hole and then put it in. It's a series of steps in order to make sure it goes in well and comes together solidly in a form that won't just unravel once it gets to the person. So you have to over excavate it. Then you have to start putting stuff in the margins, and then you're going to put a bunch of boulders in, and you have to, because the site's so smooth, like small, and the material is so big, you can't just bring in a rolling compaction like you would be designing a road. Is you have to put it together meticulously and wash things in. So you put in boulders, backfilling with the rest of the mix, and then doing that in a series of lifts so that you get everything washed in and bring it in fine. So large rock, when you put it all together, and you've seen squirrels go crawling into those voids. It's like there's a lot of open space even within that mix. You can't have that. If that's left there, it's much more likely to just unravel when the river hits it. So you have to fill all of that in. And that's where you're just literally with a hose and buckets of sand, and you're washing it in. So it's you put in a lot of boulders, and then you put in more rock. And Alex and Eric, I took a turn on it. You're just holding the hose.
We spend many hours just washing the fines. So taking basically a fire hose and washing in, and it's actually really therapeutic.
Yeah, it is.
Really addicted to it. When they wouldn't let me do it, I was actually a little shaky, but
And,
you just wash those fines in to fill in those,
and
to seal the bed.
yeah, and if the water just infiltrated, I'd be like, yeah, you haven't done enough. Keep doing more. And so, yeah, it's basically, it has to retain standing water. And going back to how much flow we have at low flows, when you're only left with maybe a single CFS in the creek at low flows, it's really important to make sure that water stays on the surface.
And we just pumped the water, the little bit of water that was coming through the subsurface, we just pumped that back in and used that for this washing in. But you can see kind of what it looks like once you get all of the sand. The excavator would sort of sprinkle the sand over the top, and we'd wash it in, and you'd sprinkle the sand over the top, and you'd wash it in, and then we do another level. And so lots of hose moving around the site. I did want to point out that I got to place that rock in the elevator, that one rock.
Well, I didn't get
You didn't have to sign off on that one.
you do that.
Yeah. So this is just working down. You can see how, this is the over excavation below, before you start placing the rocks. Yeah. Okay. Another really important part is that we Chuck and another volunteer harvested about 500 to 600 stakes, willow and dogwood stakes. And throughout the project, as we were constructing, the excavator would come in and stick the tines of the bucket in and pull back, and we'd shove a bunch of these stakes in. And you can see that right off the bat, we made sure that they were hitting the water before we sealed it back up and washed it back in. And so as we went, we put a bunch of sort of natural roughness in on the bank. And we were just out there today, and they're looking really well. This is sort of what it started to look like at the end. You can see where our goal was to hit water level at the concrete sill of the dam, which it was doing. You can, there in the previous pictures, you can see the concrete sill down here and to the top of the concrete sill. And that's Steve and Jeff, the excavator operator, basically saying, yeah, good, this looks good, great. High five. This is, yeah, this, you can see, you can think back on when that berm was running on the left side of the screen here. We have a much wider channel. We have a much, Steve's point about that stream power equation, I'm sure you've all memorized. We really got that width, to create less power in the stream. Okay. This, pools.
The resting.
Those are the resting pools. And keep in mind that we still have water diverted at this point, so there's not water coming through the stream. So this is what it looks like in January after construction. All the boards were out because they were doing some maintenance in the diversion. So in ideal conditions, this is what it would look like. This is swim through passage. And you can see all the water that is downstream. Granted, it's in the winter, there's more flow. This is looking downstream. You can see what it looks like with water in the channel. That's a much more habitable and passable, thank you. Passable channel.
Fast water, but you can see with just all the exposed rocks and more laminar flows. There's areas for like basically a path they can go up and find slow water, find little resting areas and make their way up the stream.
So, and we got out there today and took a lot of pretty pictures, and then we couldn't download them and have them for the presentation. So you'll have to take our word for it. One thing that we did, but we were able to do is Steve kind of alluded to working with a diversion owner to make some headway against that jump height. And we were able to we worked with the D mill, so hyper local to this project site, and they created some new weir boards for us that were shorter, so the 6-inch height, and then they cut a notch in it so that we could. So that creates an attractant flow that helps fish kind of find their way to where they can jump. And so we went swimming today, and we were able to get that weir board put in place. And I wish I had a picture to show you, but phones. Yeah, so that's sort of where we are today. Not quite a year after we completed the project. Post-project, we continue to do a lot of work. Steve and Liz just helped me deliver a bunch of plants. We salvaged a lot of plants as we were constructing, and they are thriving. And then we are planting a bunch of trees and shrubs there in the next couple of days. And we'll continue to monitor how those plants do. For the next 5 years, we'll be doing some pretty detailed monitoring. We've developed a monitoring and adaptive management plan that includes things like assessing the fish passage every year, the flow, the depth, taking measurements of the jump heights. We'll monitor the channel structure over time, see if it's changing, see if any new barriers come up. We take photos every year or every 2 years and see how they compare over time. We're doing some eDNA, which is basically we sample the water up and downstream from the dam, and we send that into a research lab that can determine what species are in that body of water based on DNA, like scales and things like that are in the water, which is really incredible. So we can tell, we took Kat and Cindy and I went out there and got some samples from right after we completed the project. So kind of a baseline condition. And then we'll do it over the next 5 years and see if we get new sort of blinking lights of what species are utilizing both below and above the dam. And then some other surveying that we do over time. So that was a haul. Thank you for We can take some questions. If you have any.
Are you only looking for this? Or amphibians, or, because that would have been a bigger barrier to, well, maybe it's probably, so. It might have been a barrier to some.
Yeah, I mean, I think for some, but the amount of movement I saw of some of the, like the frogs that were there, they were constantly moving throughout I think the salamanders can move throughout generally, but yeah, but not now, but I think that would be, right now, we sampled for spring chinook, coho, steelhead, and bull trout. I think that's it for now, but we might expand and evolve that over time. Yeah,
So I think that was is that once you pull out the sample, even if it's 20 years ago, you can run that for species that you maybe didn't have DNA analysis for at the time. So it's an amazing tool because we don't necessarily have the DNA structures for all of the species that we might find or might be thinking about in 10 years. And you can rerun the sample that we collected last year. You're like, oh, there's this new species wasn't present when we first time. So it's an amazing tool.
yeah, definitely trying to utilize that more.
So I find the past, the money for the watershed and most completely lost. There's probably, no way to be, like, quote, the conventional channel of look like, which seems to be true of so many. I'm just wondering about the 6-foot diameter boulders. If it's possible, those would have been in the channel in its natural state. So, of that size, they can't possibly transport boulders of that diameter. It could be eroded locally out of the hard deposits. After you encounter this 100%. Probably a large with boulders, they gradually work their way to the switch.
There were definitely some huge material, and I did a assessment upstream with ODFW, and if you continue up, there's some large material in Tony Creek, but yeah, I mean.
And yeah, there was definitely some in the berm that we were excavating. Admittedly, that creek's been manipulated a lot, and so we're not sure the origin of all of them, but also creeks have different methods of, or watersheds have different methods of transporting them. Granted, a creek this small might not just carry it in the water, but when it starts eroding around it, then it can, like, over time move rocks down, larger rocks down as well, and then also in debris flows, it's got capacity. But the size of the rock itself as well also comes from kind of basically best practices or tools of the trade. Is you kind of come up with, all right, we're dealing with flows, admittedly very conservative because we want this to stick around, and then you start looking for that median kind of rock size, and then it kind of gives you guidance on how do we then make a mix that is not just a single size, but like then some more appropriate that has various range. And so once you get that median size, then you kind of add multipliers to it. It's like, well, then we'll come up with a design maximum diameter. And that's where we're starting to get into the 6-foot diameters and bringing those in.
And Dan, I think it was you who mentioned the habitat downstream, and Steve's initial design had some root wad logs and some log structures within this 300-foot reach. And we got some pushback from the diversion owner and the potential impact to the bridge. And though we were not concerned about that being an impact, at some point we had to make some adjustments to the design to be able to move forward with the project. And, you know, I guess the way that I consider this 300-foot reach is that this is a transport reach. We need to get fish up and over this diversion. And then, as Steve mentioned, there's 5 miles of habitat, clear water, cold water habitat. And so that was an easy olive branch, I think, to offer. And then downstream of the bridge, there's a half, you know, a little less than a half mile from the bridge to the confluence with the Middle Fork. And I would really love to hit that with some actual habitat, in-stream habitat enhancement. And I think that's in our work plan for the coming years. And that will be another great stepping stone to continue to bring fish up to this point, transport them over the dam. So the design costs about 174,000. And that's about a year and a half worth of work. And then the implementation itself ended up costing about 410,000. And that includes the cost of the rock, what we paid the contractor to implement the project. Clear branch dam. So that one's a bit of a different scale.
Was there any data on historical high flows for just Tony Creek, any like winter flows, any guesses? Flood in maybe 50 foot.
Yeah, so we did basically regression equations, taking data from the Middle Fork, and then kind of scaled that to the Tony Creek watershed. I think we had the 100-year. I skipped over it because I didn't want to get into the numbers, but the 100-year was in there. I think it was about 1,000 CFS, which I think is a pretty conservative estimate on it. But the range of those fish passage design flows was more for, like 4 CFS at the low end to 70 CFS on like kind of your typical 5%.
We did have some flow data from ODFW and the tribes, but about 10 years worth. And so that was definitely worked in, but not.
There's no peak.
Yeah,
So
More typical.
we use those for the low flow, like like the statistics is, and then we did peak flow through regression. Yeah.
Can you read the stream bed wider?
Yes. Not
Skipped over that part.
yeah, so there's a lot, and different methods. One is you kind of come up with like a generic trapezoidal like cross section, not flat bottom, so you do want to kind of find a low flow that way. But then also when you construct, and this is kind of where having a contractor that knows what they're doing, but then also specifying that there's going to be some field fitting and adjustment, as you want to, through the use of some of those boulders that then stick up in the channel, is kind of force a low flow path that concentrates those low flows, and not just to a 40-foot wide swale, but in reality, when it's constructed, is you really do narrow it down to a much narrower low flow path by constricting it, and then creating those various little pools that you saw like as well. And like as we were kind of constructing it and getting it to seal up, and then seeing what we could see, which was great during construction, is there's a little bit of still flow seeping through. And then on times when they weren't running the pumps, you could actually get flows running through the constructed portion of the channel and see it. Here's like, yeah, this is looking good. So it kind of gave me an opportunity to work with the contractor going, yep, this is what, we want this. It's like, no, spreading out here, let's add some more boulders here and constrict it and narrow it up and concentrate those flows. And also, as I was mentioning though, is with it down at about 1 CFS, is at the very lowest of flows, is we are struggling to meet those depth requirements. And those depths, I think, are more for adults. like we're still trying to like maintain those passage depths for juveniles, and I think you know, talking to biologists, they're like, oh yeah, fish can, like a juvenile could get up that. Might not be like a adult fillet or salmon at the lowest of flows, but where we did meet that middle ground, and it was for those that kind of like know the statistical flow names, that we got to reach that 6-inch depth at the 75% exceedance as opposed to the 95. But we were always getting roughly about 3 inches. But in order to meet the actual ODFW 6-inch requirements, it was right around the 75% threshold.